quite prepared for it.
All right.
I do, if you want to make a name on it, but like you can read it and like.
All right, last little session for a while. We got, oh, this is wrong. It says 6.8, but it is 6.9. But still, it's the last session. Let's get through it so we have time, because this is a longer one. So listen to me. Let me teach you. I'm beginning. Is that an announcement?
There's no announcement.
I just heard.
There's announcements at 8:50.
I just heard imagining things. All right, so watch this. 6.9. Last little thing that I have to teach you for a little while, meaning no session tomorrow or possibly this week. I don't think. If anything, maybe on Friday. But we got to see how far we get in the week on Unit 7. But for now, here's Unit 6, the end of it for you guys. It's called Improper Integrals, and they're improper because it's like covers an infinite amount of area. You can see what's going on here. So what you guys are used to is like, if that's a function, you're used to getting this kind of thing where you get the area between 2 and 8. But now the types of problems we'll be interested in is like an infinite amount of area. So going from like, if that's 1 over x, going from 1 to infinity, getting all of this area. Oh shoot, I wrote an 8, but I meant an infinity. And what is basically you're wondering, does this ever get so close to the axis that it adds like a negligible, like that the final result is a finite answer? Not so I'm covering an infinite amount of space, but do I get a finite amount of area because this is so small? So it's kind of an interesting question, and it maybe looks like kind of intimidating, but it's really, really easy. It's like I'm not even teaching you really anything new today. You're still thinking of these as normal integrals. It's just the notation of it is what changes. Yeah, actually, let me leave it there and just tell you about these vocab words, converges and diverges, and then I'll teach you about like what you actually have to show on your papers. But like I said, in your brain, you're just thinking of these as normal, straight up normal integrals, just like you've been doing for the past many months. But okay, like I said, you're wondering, do you ever get finite area, or do I get an infinite area when I cover this infinite amount of space? If you get a finite answer, then you call that converging. Finite result. Like if you get 7, then it converges. That's what that's called. And it would diverge, like that means that diverging means that you got an infinite answer. Infinite result. Boom. All right, and all this stuff about limits, I'll talk to you once we do an example, but let's get into, well, let me make sure I don't want to say anything else. One or more than, okay. Left limits, right limits. Yeah, okay. I think that's all I want to say. Let's do an example. It says, determine whether this converges or diverges. Okay. So, like I said, you're thinking of this as a normal integral like you've been doing. I'm going to take the antiderivative, I'm going to plug in infinity, and I'm going to plug in 1. That's what's going on in your brain. But on your paper, you can't write that I'm going to plug in infinity, because that's not a number that you can plug into a function. So that's why you saw those limits before, where you have to say on your paper, you have to say, I can't plug in infinity, but I could plug in a number, b, and see what happens as b gets bigger and bigger and bigger and bigger. So in other words, you're taking the limit of the upper bound as b goes to infinity, like the upper bound goes to infinity. But that's the only thing that's different. This used to confuse me when I first learned this, and I didn't know if I fully understood it. But hopefully I'm convincing you that this is no different than anything. You just take the antiderivative, plug in b, plug in 1, and then you check what happens as b gets q. Okay, so let's do it. Let me not forget my limit as b goes to infinity. And then, like I said, antiderivative of 1 over x, you remind me what that is. Oh, nice, y'all. All right, natural log of x evaluated at b and at 1, so this will be the limit as b goes to infinity of natural log of, here's me plugging in the b, here's me plugging in the 1. Okay, and then you check what happens when b goes to infinity. So, like, here's kind of your result, but I got to decide what's going on with this limit, and that'll tell me whether this converges or diverges. Okay, so one of these we already know, natural log of 1, we already know that's 0. But do you guys know what happens as b goes to infinity? Natural log of b. Nice, I see you gesturing. Nice. Yeah, okay. Yeah, this is another time when it's good to know parent functions, but natural log looks like this, that's the graph of it. And it's growing really, really slowly, but it is growing, it is going to infinity. So the natural, like, basically the bigger number you put into here, the bigger number you'll get out, without bounds. So, natural log of b would go to infinity, minus 0 if you want to put that, but final result would be infinity, meaning we took the area, here's 1 over x, we took the area from 1 to infinity, and we were wondering, does that give me a finite answer? And the answer is no. So then let me make sure you heard what I was saying before. Does this converge or diverge?
Diverge.
Okay, all right, good job. That was the problem a few years ago. Like, I didn't teach that good enough, like, or make a big enough emphasis on what that meant, so people were always asking me, what does that mean? But yeah, that's all there is to it. If you get infinite, it diverges. If you get a finite, it converges. Both of these are coming off, these little ends. All right, I'll mess with it later. Okay, same idea here, e to the x from negative infinity to 0. In my brain, I'm just thinking, okay, I'm going to take the antiderivative, I'm going to plug in 0, I'm going to plug in negative infinity and see what happens. But on your paper, you have to write it more formally, so you have to, like, you have to say, I can't plug in infinity, but I can plug in a number and see what happens as that number goes to infinity. So let me take the limit as a goes to negative infinity. To 0, e, dx, dx.
Does it need to be like different from b? Is that just like?
Yeah, no, I was just gonna say that this was like, this might be, I don't know if every teacher does this, but I call the lower bounds A and the upper bounds B, but you can just always call it like whatever you want, C for both of them, whatever. Yeah, I was just thought as I wrote it, I was like, somebody's gonna ask about this.
Isn't it X a lot on the AP test? Like, it'll be, I mean, it's just like a variable, on like some of the practice test questions that I did. It's just like X.
Oh, yeah, of course, yeah. But then you're probably seeing just straight up limit.
Yeah.
Limit, question. But here, since there's already an X,
Oh,
for the
yeah.
people in the video, the question was, can you just make it an X? But here, since there's already an X, you probably want to use a different letter. All right. All right, so like I said, antiderivative of e to the x would be e to the x. Plug in the 0, plug in the a I meant. And then I already messed up because I forgot the limit bit. I messed up again, that's negative infinity. Okay, and then here's me plugging in 0. Hang on, I messed up again because I forgot the limit. Oh, good lord, it's not my day. That's an e to the a.
Do you need to write the limit for the first one, or can you just write the second
It's
one?
like, I guess you can just write it on the second one. What I'm saying is the limit of that whole thing.
Okay.
But you're right that that's the same thing as putting it on the second.
Okay.
Okay, and then e to the 0, well, let me just write one more.
Yeah.
E to the 0, we all know is 1, I hope. But e to the negative infinity, do you guys know that limit? What happens to e as it goes to negative infinity?
Exponential function.
Exponential. Okay.
Yeah.
Yeah, I don't know if you're still thinking or if you guys heard Sam Flynn, but e to the x, again, it's just good to know parent functions, because e to the x goes like this, so e to the negative, as you go to negative infinity, this gets closer and closer to 0.
Mm.
This will go to 1 minus 0, which is 1, as I hope you know, and therefore, well, here's the result of the integral, but to answer the question, does it converge or diverge? Of course, I got finite numbers, so they converge. Okay, that's kind of all there is to this section, but there's a lot more examples because these can get really annoying. Like if you have a vertical asymptote or whatever, you have to be careful about how you label this, your integral. Okay, so look at this first one. Here's what I mean by when I say these are really annoying. This first one, if you're going from negative infinity to infinity, like taking the whole entire Cartesian plane worth of area, then you have to split it twice. You have to do, well, let's get into it. Yeah, but you have to do limit for the lower infinity and a limit for the higher infinity, and then go from there. So here's me splitting it. Limit as a goes to negative infinity. I don't know if I should write an in-between step, but I will if you need it. But I'm going to write it like this. A to 0 plus 0 to okay, like I said, I'll write an in-between step if you need it, but I'm going to skip as much as I can just to get through this. We got a lot of problems to get through. I'm going to write it like that. But the in-between step I was going to write is that that's the same thing as splitting it from negative infinity to 0, 4x cubed dx plus from 0 to infinity 4x cubed dx. And then that's why I wrote it, oh, this negative infinity, I have to replace that with like a constant and see what happens to the constant as a goes to infinity, and then same thing with the second. Question.
You have to use 0, that's like the easiest one.
Nice, good job. I meant to talk about that, but yeah, no, there's no reason for using 0. You could use negative 10 if you wanted to, but yeah, that's 0. That's obviously nice. Okay, all right. Now, well, let's get this result, and then I'll say something about the intuition for this. Like something you got to be careful about. Well, okay, so let's just deal with one of these. Let's deal with this left one. Well, I guess this is all ready. There's nothing for us to do other than take the antiderivative and start plugging stuff in. So antiderivative of 4x cubed is, you tell me. Nice. Okay, all right, good job. The limit is a goes to negative infinity of 4x to the 4th over 4, which is just x to the 4th. Okay, and then, well, I guess maybe I should write this other one. But I'll worry about that second one in a second. Let me just deal with this one. So let me plug in the 0 and all that. X to the 4th. Oh shoot, I meant 0 to the 4th. minus a to the fourth okay. And now here's us evaluating this limit. 0 to the fourth is obviously 0. But what happens to a to the fourth as a goes to negative infinity?
Goes to infinity.
Nice. Yeah, good job. Again, think of the parent function. A to the fourth is like a parabola. And so as you go further and further left, this goes up and up and up and up. This would go 0 minus infinity, which would, of course, be infinity. Okay.
What would you say if A was like the third or an uneven or an odd like power? Because it would keep
I
going
guess
down.
it go down, so negative infinity. Okay. All right. And then watch this. You can just stop here because the definition for when it would converge, like an integral like this that goes to from negative infinity to positive infinity, the definition is that what only converges if both of the things converge. I'm trying to look for it. There it is. Both of these have to converge for one of these to be for one of these integrals from negative infinity to infinity for that to converge. So I'm just going to stop here. I'm not even worried about this. Don't care. Because once I get that one of them diverges, the whole thing diverges.
No, I didn't.
Okay. And then we're done with that one, but just to make you think a little bit, 4x cubed, you may or may not remember that looks like this. So maybe this result kind of bothers you because I don't know if you can see what I'm getting at, but if you go from negative infinity, boop, 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 get all this area, to infinity, boop, 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 get all this area, then, I mean, yeah, exactly. Since it's an odd function, as in it's like reflected but upside down, like it's the same on the left as on the right, but negative on the left, you would think that your result would be 0, but that's just not how this is defined. But to account for that, there's other definitions that you guys don't have to learn yet. They're just like fancier, like graduate level math, where this is defined to be 0, but you don't gotta worry about that. So that's just for fun. Cool. Anyway, our answer correct. Diverges. We're good. Close your ears if you're not interested in the higher ones. All right. How many more do we have? Oh yeah, one where it's an asymptote.
Like, it doesn't matter.
And one of those.
If the other one is which it would be
Just
I don't remember that.
Not logic.
not logic. Definition. Okay. So it's
All right, well-
both have to either be
Divergent
Yeah.
or convergent or
Yeah.
one divergent.
yeah.
Okay.
So then it's we got this.
So here, there's nothing different. We're doing the same thing. It's just instead of the infinite area, like resulting from you going to infinity, here we get an infinite area because of a vertical asymptote. So 1 over the square root of x from 0 to 4. Of course, that would have an asymptote at 0. It would look something like this. So you're trying to get that area that I shaded in. And so that's where the improper part of this integral comes in, is that this is an infinite amount of space that you're covering. So again, you deal with it the same way. You're not like, it's improper to plug in the actual 0 because that was like make this undefined. Well, you can plug in the 0, or you can plug in a number and see what happens if that number goes to 0. So this will be the same as the limit as a goes to 0 of the integral from a to 4. Okay, like that. But the only thing I'm missing is that this asymptote happens as I approach zero from the right. I don't think that's a problem in this case, but sometimes you might get to like some weird things. Like for 1 over x, you get that sort of function. So you want to be specific about which way you're approaching zero from. So approaching zero from the right, since I'm going from 0 to 4. If this was a right limit, then I'd be approaching zero from the left. And we do it slightly different, but that's what we got in this case. And then, like I said, it's the same thing as always. You take the antiderivative, you plug in the a, and you plug in the 4, and you see what happens. Okay, but the antiderivative of 1 over the square root of x, you didn't know it off the top of your head? Yeah, okay. Yeah, that's what I figured. So it's easier to write this as x to the negative 1/2. Unless you have a lot of foresight and you could do that in your brain, I think it's helpful to show this step. Okay, but now that it's written as x to the negative 1/2, now it's like not that hard. So you can add 1 to the power, and it becomes x to the positive 1/2, and then divide it by the new power. So divide by 1/2, or in other words, multiply by 2. And now plug in your 4 and your a. Okay. And then here's one that's not even, you don't even really got to know parent functions, because this is like, as a goes to a number, so you can just plug in the number and you're good. So like what I mean is 2 times 4 to the 1/2 would be 2 times 2, which would be 4, minus, and then if I plug in 0 to this a, I'll get 0. There's no like undefined nature of this or whatever. This is just straight up like square root of 0 is 0. So this part will go to 0. You get 4, and then to answer the question, this converges because I got a number. Nice. All right, and then this tangent one. I guess let's just do it. Let's just do all of them. We have the time. All right. Yeah, this tangent one, you may not remember, but you might, that since tangent is sine over cosine, since tangent is sine over cosine, the cosine is 0 at pi over 2, so tangent is undefined at pi over 2. So it has this vertical asymptote at pi over 2. Tangent looks like this. And so what's happening is for this area right here, boop, 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 boop. So you can see the infinite nature of it, and that's why this is an improper ratio. So just like the last one, oh shoot, this is a vertical asymptote, so I have to take the limit as pi over 2, or sorry, as b goes to pi over 2. And then that would be from the, approaching from the left. I'm going from 0 to pi over 2. All right, cool. So I got to take that integral, but that is kind of a tricky integral to take if you don't remember how to do it. Do you guys have any ideas? You actually have done this before, but it was before winter break. You know? You know? You know? I don't know that. I don't know what you're saying. What is You might be right, but I can't tell. What are you gonna say, James?
Can we do that? Can we did it earlier where it's like the tangent? You want to talk about like, I forget what it's called.
Was it B?
By part.
I wonder if you could. In my brain, it feels like you might be able to do that. Well, no, maybe not. Because no, that's not what I had in mind. It's simpler than that. It's an A/B concept. If you do U substitution and you make U be code, then
Oh my god. I did not know how to do U substitution 2 weeks ago before I had to relearn U substitution for the final.
all right, here's me. This is me going fast, but let me know if you need the reminder. Where you make U be cosine, that way du is negative sine, and then when you solve for dx, the signs will cancel. So here's where we are. Limit of b goes to pi over 2 from the left. 0 to b. Here I'm showing all my work, but you guys could probably skip this if you see what's going to happen. Cosine was u, dx was negative du over sine. Okay, and so I get negative b cancel. So negative 1 over du. All right. Okay, and now this would turn into the antiderivative of this would be limit as b goes to pi over 2 from the left of negative natural log of u evaluated at b and 0. But let me change that u back to a cosine before I write that. That would be improper. I technically should change these bounds to start with. But since I didn't, I can salvage it by going back to cosine again. At b and at 0. Okay, and now we're almost close. Now we just take the limit as b goes to pi over 2 from the left of negative natural log of cosine of b minus negative natural log, so plus natural log of cosine of 0. Okay, and then finally, actually, let's do this. Don't write what I just wrote. Erase that cosine because we can evaluate that part at least. Cosine, okay, if b is going to pi over 2, then cosine is going to where? Well, what's the cosine of pi over 2?
0.
Yeah, and it's approaching pi over 2 from numbers smaller than pi over 2. So it's going to 0, but from positive numbers. Because here's the unit circle, I'm approaching pi over 2 this way. Whoops, like that. So this is approaching 0 from the right. So yeah, my notation is now terrible, but it's just for teaching purposes. Let me write it like that. And then plus the natural log of cosine of 0 is 1. Okay, and then now do you know what happens? Maybe I should, well, I'll talk about my notation, because I wrote a lot of stuff that you would take to get points taken off of for the AP test, because I wrote some bad stuff. But we'll worry about that in a second. But for this blue part, that's going to this blue part. And do you know what natural log does as it approaches 0 from 1? Remember the... Yeah, nice. Yeah, again, we talked about it in a second ago. But natural log of x looks like what I just wrote here is nice, circled in green. That's natural log of x. So as I approached 0 from the right, this would go down to negative infinity. So this blue stuff would go to negative infinity, but still goes to infinity minus or plus 0. So final answer infinity, and now final answer is that this divergent. All right. Last one, I skipped this last year, and I don't regret it, because this is just about to be like where we have to split it in half, because you can see what's going to happen is 0 to 2, like 1 falls between 0 and 2, and 1 would be the vertical asymptote of this graph. So we're just about to do 2 of the ones that we just did, where we have to do one from the left and one from the right. And I don't know if we have time.
Is there an easier way to like tell if the conversions that I use like yeah,
Not that I know of. I mean, unless you have really good foresight and you're like, the AC derivative will be this. What's that limit? Like just doing it in your head. But no, not just by that I know of. No, not really. But maybe some people know some truth. Yeah.
If you're answering a question, do you have to say like if it's converging, do you have to say what the number is, or do you just like put up a guess and say converging?
Most of the time they'll ask you like the way they'll ask you on the AP test is like evaluate this integral or say that it's divergent. So yeah, most of the time they'll want the number because that was a good question. All right, so I think we have 4 minutes. That's going to be long. Like you guys just saw that we spent like 5 on this one alone. So this one will just be 2 of those. It's no different. You just, like if you're trying to do this by yourself, you would have to do 0 to 1 plus 1 to 2. Like that. And now it's just 2 of the same ones that we just did, where you split the limit for the 1, you split the limit for the 1 over here, and you do 2 of them. And I don't remember the answer to this, but I could do it and let you know later. But yeah, I think people have to get to their classes. I think that this one's not worth your time. Let's be done. And again, don't come in early tomorrow. I mean, unless you want to, but I'm not going to be teaching early tomorrow. I'll let you know when the next session is. Great job, y'all. I'm here for questions if you need it.